glance at this homework right here that you have in front of you. The problem, though, is I get some students who look at it, and I personally do the same thing. I just kind of glance at stuff, and I don't always take a really good read at it. But this one says here, decide if the following statements are true or false. Okay, but if it's false, then make the correction so that way it becomes a true statement. Now, to be honest, I have some students who do this, and then they corrected it in a different way than I corrected it. That's okay. Kind of like homework number 1, there was more than one way that you can analyze what they were doing wrong safety-wise from Unit 1, homework number 1. So I'm just going to show you as an example over here. It says that Rutherford performed the cathode ray experiment. Rutherford performed the cathode ray experiment. Well, this we already talked about in our notes already, but I'm going to pull open our notes, which looks like this, and I'm going to go to the cathode ray, or you can go to Rutherford, either way. So here's Ernest Rutherford, and he actually did the gold foil experiment. False statement. Or you can go to Thomson, and you can go to the cathode ray experiment, and it was J.J. Thomson. So it depends on how you make that correction. But either way, that is, I agree, a false statement. But there's 2 ways to correct it. So don't get upset when I show you my answers or the way I did it personally. I personally went ahead and changed it, and I said, instead of Rutherford, I just did the first mistake, and that's what I did, and changed it. And I said, it wasn't Rutherford that performed the cathode ray tube. Here's a cathode ray tube, and the cathode ray tube was J.J. Thomson. So I went ahead and just changed it that way. Thomson. Okay, so reading letter B. Letter B says the electron was discovered first, or discovered before the proton, which is true. We kind of talked about why. It's because when you're discovering something brand new, you normally explore or discover, and you see the outside portion first before you go inside and inside and inside to discover more and more and more. So that's a true statement. I'm just going through a little bit of the homework itself, and that's it. Then we'll go back to our notes. The next one, Dalton's work. Oh, let me pause for a moment. I'm going to go to Dalton. And so Dalton is over here. He was one of the earlier people. So Dalton, it says here, Dalton's work is credited with being the beginning of the modern atomic theory. Well, Dalton is considered to be the father of modern atomic theory. That's true. That's a true statement. He gets that credit for being, and again, we don't use his. And after his idea of the atom came here J.J. Thomson. Then after J.J. Thomson comes Ernest Rutherford. After Ernest Rutherford, then comes over here Chadwick. And after Chadwick comes Niels Bohr. And even then, we still don't use any of their stuff. So even though Dalton was considered to be the modern, we don't use any of their information. Theirs is still not correct, and that's only because of modern technology we found out that they were incorrect. Then number 2 says, go ahead and fill in the chart. So it says here, order of discovery. Well, I know that the proton was discovered second, the electron was discovered first, and the neutron was discovered third. And the reason why the neutron was discovered last, because there is no charge to it. But remember, Chadwick knew that there was something mass-wise in there, but it was quote-unquote invisible. We couldn't figure it out. Okay, we couldn't figure it out because there was no charge to it. So we couldn't see what it was because we didn't have the technology, but we knew mathematically wise when you put it on the scale, it wasn't mathing out. There were missing some mass somewheres. There was something, which then he was correct. Chadwick was right. There was this neutron that has 0 charge, but yet it does have mass. And then the location and charge of it, you're just filling it out. And then after that, let's look on, I'm going to come over here for an example on question number 3. Question number 3 says, which 2 parts of Dalton's theory, remember Dalton's over here on page 1 of our notes, Dalton's theory of the atom were later shown to be wrong and why? So they just want to know which 2 parts. Well, remember, we actually have 1, 2, 3 parts that are false. Okay? Part A, all matter is comprised of tiny individual particles called the atom. Completely false, because later on we have Thomson as well as Rutherford that proved, and Chadwick, that proved that atom is made up of different individual parts, not indivisible, individual. So the electron, the proton, as well as the neutron. B, it's also false. All atoms of an element are identical. Well, we haven't talked about it just yet, so you don't know that information, but that part is false. We have other elements, other atoms of hydrogen. There's more than just one type of hydrogen. They are called isotopes. So you can't really necessarily put that as an answer because you don't know how else it was proven just yet. And then part C, atoms cannot be created, divided, or destroyed. Well, yes, I will say somebody in here earlier this week said, hey, we've got like nuclear bombs and you can divide them. And then, hey, whether you know this or not, over in Sweden, we got it's called an atom smasher. It's located miles underground. So they take an elevator under the ground to this big, giant, circular thing that's called an atom smasher. And so they get atoms and they make them rotate in a circle really, really fast. And what happens is they put another one in front of it. So when the atom comes around, bam, it smashes literally into the other one. And they're trying to create new elements. Well, to be honest, if you look at the periodic table, which we haven't really talked about this portion just yet, but these elements on the periodic table over here, these are man-made elements that do not stay together very long. These are atom-smashed elements. That's why they're over there. They're actually atom-smashed elements that don't stay together. They may stay for a split of a hair of a millisecond, and then it falls apart. They can't stay together that long, okay? But yeah, they're able to smash them together and quote-unquote create, I guess you can say, but divided. Yeah, an atom can be divided. So for an example, letter A and letter C. And why? Well, why? Because we know that Rutherford, as well as Chadwick and Thomson, discovered, because later other parts was discovered, or however you want to say it. But other parts were discovered. The electron, the proton, and the neutron. So yeah, it can be quote unquote divided into other individual parts. Alrighty, so that's the part over here, part 1, or page 1. Page 2, which we need to do some more notes, I understand, before we can actually finish this part right here. But I want to take a glance at it. So it says SR, you're going to need the periodic table, and everyone should have this little packet right here. So let's go to strontium, which is SR. SR right here on the periodic table. I'm going to go ahead and scroll in so we can see it a little bit better. This is part of what we're doing in our notes today. It says here, what is the atomic number? We talked about this briefly earlier this week, and the atomic number is that top number at the top, which is going to be 38. The atomic number is 38. Again, if you don't have your homework out, not a problem. I am going to try to take pictures in a little bit and post it on D2L for us. Next one here, they want to know the proton number. Well, we said that all atoms are considered to be electrically neutral. And the atomic number not only tells me my proton number of 38, but because all atoms are considered to be, and I even highlighted this section, electrically neutral, then that means that it also has 38 electrons. But I did say, unfortunately, atoms don't stay like that, okay? Atoms are considered to be electrically neutral. Oh, they're like cute little babies. But they don't stay cute little babies forever. They grow up to, teenagers and adults, and so they don't stay as cute little babies forever. But they are considered to be electrically neutral. I did mention, hey, for us to figure out what the neutron number is, we get the atomic number. And I'm not sure, I do not believe that I said this earlier this week, but I think when I set this on a number, for an example, I think it was like Christian that spoke up. Let's look at number 19. Christian, what would be the atomic mass, which is that number at the bottom with the decimal points, for 19, potassium?
39.
39. I agree. But for an example, SR is 87.62. In that situation, we round up. One more time. I agree with Christian 1,000% that K has an atomic mass of 39. But whenever we look at it chemistry-wise and we're looking at the mass, when it has a decimal point, we round up. Easy cheesy? So let's go ahead and let's do that. We want to figure out the neutron number over here. So I'm going to go ahead and get the number 88, take away 38, and my neutron number is, go ahead and give it to me, 50 even? There we go. There goes my neutron number. Easy cheesy. We're still at easy cheesy mass. Now the isotope symbol is what we haven't talked about yet in our notes, and so we're going to need to do that in just a moment. Let me go ahead and do one more. Let's go ahead and do one of these that doesn't have the symbol. For an example, let's look at this one, 15. It has 15 protons and it has 15 electrons. Heck yes, it should, because all atoms are considered to be electrically neutral. Do they stay neutral? No, they end up becoming ions. But right now, we consider them to be electrically neutral. So this proton number or this electron number, let's go and look and find number 15 on the periodic table. Here is number potassium. Phosphorus, okay, phosphorus, number 15. So phosphorus, number 15, here it is, letter P. Atomic number, oh, wait a minute, I don't even need the periodic table because the atomic number is the same number as protons, which is 15. I don't even need that periodic table. And now it says the neutron number is 16. Now, wait a minute. This is where things might change up and may not match. If we look at phosphorus number 15, this has a 31 as the mass number. 31 take away 15, what is that number? 16? Well, then we look good. 16 plus 15 equals 31.
Wait, so we like kind of round up?
We do. We need to round up or we leave it as is. So I'm going to go back to that example. When Christian said 39.098, he rounded it and left it at 39. I agree 100%. But SR is 87.62. We rounded up to 88. Yes. So if need be, you will round up or leave that number as is because of the decimal points. So I just wanted to go over that homework with us, and then the rest of us should make a little bit more sense once we do our notes. That's the reason why our homework is not due until later on this week. So I'm going to move this now out of the way. I'm going to keep my periodic table here because I know we're going to need it. I'm going to get my notes out because I just really wanted to kind of go over a little bit of notes with us for a moment. Yes.
The periodic table, oh wait, it's in our notes, correct?
I don't think it's in our notes. I think
Well, it's right
last.
here.
Oh, you have one in your notes? I think we definitely grabbed one when we were, before when we took our quiz from last week. Like I stapled it. Yep. The reference material. Yeah. So I think we all like just grabbed one, and I wanted y'all to keep it with you. But believe me, I have definitely more and more and more. I can always give you more if you need some more.
Yes, I might be.
Over there by Andrew. Andrew, open up that door. To the left, there's like these little shelves, all the way on the third shelf on the left. And on that second shelf, go down to the third shelf. 1, 2, 3. Over to the left on that third shelf. See those little shelves? No, up. No, up again higher. All the way higher. There you go. Go down to like the second or third right there. Somewhere's around there. I don't know where it's at. If that's not it, then look up. There you go. Are those the things that we had before? Yes. Here you go. Grab a whole bunch, and whoever wants some, there's some more. 3 extras over here. Whoever wants some, you can have as much as y'all want. I can make more copies. Right? And just keep them inside your folder. That's okay. Oh, okay, gotcha. Oh, look, that's very nice. He's trying to give you a picture that has some understanding. Two copies, and then pass right to the back. Pass that. Yeah, yeah. We can call them down. Well, you should.
How so?
Just, you're in class together, and y'all are gonna be here at this school, this college for the next few years. You never know when you're gonna need somebody later in the future. What if next year you need to ask them for assistance on some notes or something? Hey, you? Hey, you is not always the politest thing to do.
Excuse me, may I-
Excuse me,
may-
Addison, be personable and show people, that you thought of them. You want me to think about you and know your name. Same way with everybody else. Just saying. It's that human nature.
I would have thought of this, you know my name.
Do all professors? Continue to go to college. Continue to go to college and let's see what happens. Unfortunately.
You gotta make it the name stand out first day. My professor, he doesn't know my brother's name, but he knows my name. Every professor I've ever had, they know my name.
But he stands out.
Yeah, because I'm one always asking questions.
There you go. There you go.
They
Exactly.
really dumb stuff.
But at the same time, it's good to have that connection with other people around you. You never know when you've got to ask somebody something. You never know. You never know when you need to build that bridge, or you needed that bridge to make the connection, but you never built the bridge in between people. Got to build that bridge between people. Just saying. Here we go. Addison, Yakayla, and Christian. We should know each other's names. All right.
Have a name.
Whoa! You call me. Oh! So I'm going to tape it to the back, and if you don't know, I'll then turn around?
Yeah.
Yeah? Christian, what's my name? Okay, you win. All right, here we go. Notes. We've got to get their notes so that way we can get homework done. And again, like I said, Friday, I would like for us to practice pipetting. So, I don't know. Maybe we should make a game of it. Ooh, that might be good. Who is the most
Who can make
accurate?
explosive content?
It's water, Christian. H2O. Golly. It's water.
I wanna see some water explode.
We'll say that that's how they get the space shuttle to go into outer space. It's hydrogen and oxygen, and when they combine them, that combustion right there causes it's steam.
Hydrogen bomb.
Hydrogen bomb. Elephant tooth. That's not even explosive. That just gets big. Yeah, it's not. Okay, no bombs, no bombs. Oh, we're videoing. Okay. Sorry, Calm. That's not what we mean. We mean theoretical emotional bombs. That's just as bad. Here we go. Let's go ahead, and this is where we ended up with our notes earlier this week. I might be wrong, but this is where I think we ended up at. So take a glance at this section right here in our notes. It says here that, hey, don't forget, I said it a couple of times, all atoms are considered to be electrically neutral, meaning that they have the same number of protons as well as electrons. Now, when we look at that atomic number represents the proton number. One more time. The atomic number equals the proton number. The atomic mass equals the proton and the neutron number. Okay, the atomic mass equals the proton and the neutron number added or combined together. Now it says here, Bohr, though, going into the Bohr model, he likes to go ahead and represent his electrons in different orbitals. Remember? That's what Bohr said years ago over here. He says that electrons are in different orbitals or energy levels. Okay, this is going to come back to us later on a next unit. We'll talk more about it. But when it comes to his orbitals or energy levels, he says that, for an example, if we have an oxygen atom, okay, I'm going to go to the periodic table. I'm going to find oxygen over in the nonmetals, and oxygen has an atomic number of 8. Now, that 8 tells me the number of protons. All atoms are considered to be electrically neutral. So that means that he also has 8 electrons. So the way we draw a Bohr model is in the center, we're going to go ahead and have 8 protons. In the center of the nucleus, we need to find out how many neutrons, because remember, the atomic mass, let's look at it up here, the atomic mass tells me the added amount of protons and neutrons. Now, if I have 8 protons, then that means that I also have 8 electrons. So 16 take away 8 equals, there we go, neutrons. So there goes my nucleus of my Bohr model. So I'm going to go ahead and circle my nucleus because that's what's inside my nucleus. Now, Bohr said, one more time, I'm going to turn the page. You can stay right here. He says over here that, you know what, I believe that our atoms are organized in a system that has them where the electrons are arranged in 7 circular orbital paths, kind of like we have the sun and the Earth and all the other planets orbit around the sun. He believes that the electrons orbit in a circular path around the nucleus, So here we go. First path, or the first orbital. The first orbital, he stated, well, I believe that the first orbital is the lowest energy level, and that low energy level can only hold or can only contain 2 electrons. There they are, 2 electrons. Now, if my atomic number for oxygen equals 8, and my 8 not only indicates the number of protons, but all atoms are considered to be electrically neutral, so that means that this oxygen atom must also have 8 electrons. And if I use 2 on the first orbital, 8 take away 2 equals 6 left over. And he stated that my second orbital can contain up to 8. And the way we arrange them is that because negative and negative want to, what does negative and negative want to do? Repel each other. We like to first always spread out my electrons. So one will go on one side, the other one will go on the opposite side. That's 1, 2, 3, 4. Oh, I need to put 2 more. 5, 6. So I try to spread them out. We'll talk about where electrons actually sit. I refer to it as a bus and the seats on the bus, but that's not going to be until next unit. So we try to spread these electrons out 1, 2, 3, 4, 5, 6, or 5, 6, but we spread them out the best we could because negative and negative is going to want to repel each other. Okay? So here is what, or how many electrons can fit in the orbitals. A lot of students do forget that the 4th orbital actually, quote unquote, contains 18. That's a little secret, okay? Traditionally, all students have been taught that the first orbital contains 2, the second orbital contains 8, the third 8, the fourth 8, the fifth 8. When you're in middle school, they just tell you 8, 8, 8, 8, 8. That's it. The true story, though, in chemistry is that the 4th orbital could contain 18. But that's not until next unit why we'll talk about that. They're called hybrids, and we'll talk about these hybrids of these electrons on how they sit in these energy levels later on. So we just take that into our mind, accept it, not knowing exactly how it works. How can I help you?
Is the next orbital a higher number of electrons? Okay.
The 5th is going to be 8. We'll talk about those orbitals. That's not until next unit. But the 1st, 2nd, 3rd, 4th, traditionally it is 8. There's a little secret, and the 4th one is 18. But we'll talk about those orbitals. You're right, it does get more and more and more. It does. But that's not until a whole nother unit. It says here the lower orbitals must be filled before we get into the higher energy orbitals. So yes, Acosta is completely correct that the first one is 2, the second one is 8, the third is 8, the fourth is 18. True story, it does become more, but that's because it has higher energy levels. Okay? But the way we feel the energy levels is that we fill the first one first. Then after the first one is filled with 2 electrons, then we can go to the second one. After the second one is filled with all 8 electrons, we can go to the third one, and we can fill more 8. Now traditionally right now, we're just gonna fill 8 in all of them because we truly don't know how they fit 18 or any more. Okay, we don't know yet. So it says here, oxygen, who has an atomic number or atomic mass of 16, forgive me. This is the mass number, okay? That is the mass number. Oxygen has an atomic number of 8, but when it has a dash like that, that's indicating the mass number. This, I know that on the periodic table, it has 8 protons, meaning that it also has 8 electrons because all atoms are considered to be electrically neutral unless they tell me otherwise. And the neutron number would be 16 take away 8, which equals, I agree. So it has 8 neutrons. And we drew it on the previous page. Now, valence electrons, I'm not sure, but I'm pretty sure you probably heard of that word prior, like in middle school. But the word valence electrons are always going to be the outermost electrons, or the outer energy level. How many electrons are on the outer energy level? Now, if we go back to that previous page when I drew out this oxygen and the Bohr model, this is called a Bohr model, my outer energy level has 1, 2, 3, 4, 5, 6 valence electrons. Oh, wait a minute. Let's take a glance real quick at the periodic table. Oxygen so happened to be in group 6. Every element that's in group 6 has a valence electrons of 6. Every element in group 7 has 7 valence electrons. Every element in group 8 has 8 valence electrons. Oh, do you not see the order to this? How amazing is my periodic table? Okay, so it says here the most electrons needed, it says here, is going to be 8 to fill it up. So we need 8 valence electrons for an atom to be happy. But wait a minute, Miss Munson, you just said on energy level 4 on the previous page is 18. Remember, that's like a little exception to the rule. We haven't gone into most detail. In our mind, we are just going to call it 8, 8, 8, 8, 8. Okay? In our mind, we're calling it 8, 8, 8, 8, 8. We haven't gone up to that next level yet of talking about it. It says here, let's draw a Bohr model of sodium. Okay? They even told us the neutrons, the protons, as well as the electrons. So sodium, when I draw my sodium, I'm going to start off with the nucleus of 11 protons. I'm going to have the nucleus of 12 neutrons and draw my nucleus. The first energy level can only have 2 electrons. It's a lower energy level. It cannot hold a lot of electrons. So if I have a total of 11 electrons, 11 take away 2, now we're at 9 electrons left over. Okay, so obviously I have to draw a second energy level. And in that second energy level, the max it can hold is 8. So let's draw them in. 1, 2, 3, 4, 5, 6, 7, 8. 9 take away 8 electrons comes out to 1 electron left. So now we're going to draw another orbital or another shell, and we're just going to fit in 1 more electron. He's by himself. He's on the back row by himself. Bless his heart. Oh gosh, I was just gonna.
You're a loser too.
No. I hope y'all go back and revisit these videos when y'all are older. And then, how funny is that gonna be? Christian talk about his fake twin that comes into class,
And then he said, and then he's like, Miss Munson, I need to go get a snack or I'm hungry. And then it's all video. And it's going to be a little funny when y'all are 32 watching this.
Can I go get a barbecue sandwich real quick?
Can I get a,
Honestly, I'm not sure if I would.
Is that a barbecue truck?
that was 2 weeks ago. We're past the
They're
barbecue.
there again.
They are.
Yeah,
That's going to be later.
they're out there.
Sweet.
And Miss Munson talk about Santa doesn't exist. Oh man, I'm crushing.
Santa's real.
Santa's real. I want y'all to revisit this video later.
That one time, his mom was literally
How many valence electrons does an atom of sodium have? One. But here's how we write the symbol for valence electrons in chemistry. 1 VE, 1 valence electron. We shortcut. We do a lot of shortcuts in chemistry. It says now draw sulfur. So you draw sulfur, I'll draw sulfur. I don't want you to cheat off of it.
You want to draw the gas, liquid, or the solid?
This one right here.
Oh, the Bohr model.
Bruh. Overall, you'd be yellow.
Okay, so do yours. I'm going to draw my sulfur. Sulfur has 16 protons. 16. Oops, I almost messed that up.
There's 3 of them now.
All right, 16. Take away blank. One, two, three, 4, 5, 6, 7, 8.
6, 7.
No, 8. 8 is how many valence electrons? Okay. 1, 2, all right, here we go. Oh, I got 6.
Hey, I got 6 too.
Woo woo.
He wasn't done.
Oh, sucks for him.
Now I got the answer.
Now, alrighty, so Bohr model, pretty easy cheesy. I think we're okay with that. Do we use the Bohr model? No. Bohr, we don't even use it. But either way, that's the Bohr model.
Yeah, it's boring.
I want your children to watch these videos later.
I'm not happy. I hate
Just in case.
the bloodline dies with me. The bloodline dies with me.
Just want to make sure that we are all on this. Let's keep going. Next one over here. It says this would be more like the quiz/test. Can you tell which of these Bohr models are drawn incorrect? So let's go ahead. Letter A. Take a glance at letter A. A is right. Whoever said that. B.
No.
Nope. C.
Yes. BB gun?
C is yes, right. D.
Yes.
D is correct as well. The only one that is incorrect is letter B, and the reason why is because,
It only has 1 electron in the first thing.
yep, it has 1 electron in the first shell or energy level. Because it has 1 electron in the first shell or energy level. It should have 2. You've got to fill the first energy level or the first shell before you can go to the second one. Kind of like if you go on the school bus and the teacher or the bus driver's like, hey, you got to fill in the first row before you go to the second row. Then you got to fill in the second row before you can fill up the third row. And then if you want to sit with your buddy, then you better make sure you're in line together. Alrighty, let's turn the page. Now, there's a difference, though, between the Bohr model and the Lewis dot structure. One more time. There's a difference between the Bohr model and the Lewis dot structure. The Lewis dot is what we currently use to this day. We, yes, like Lewis. We, no, do not like Bohr.
Blue boar.
Boo Bohr, yes, Lewis. Lewis dot diagram is arranged, it says here, to where only the valence electrons are shown. That's all I need. To be honest and truthful, the valence electrons where all the bonding is occurring. So when we do our drawings on next unit, unit 3, we're going to do only Lewis dot structure. When we're trying to bond elements together to form a compound, we are going to do this in the Lewis dot structure because all of the reactions occur with the valence electrons. They're the ones that are doing all of the bonding. Okay, one more time. The bonding is occurring with those valence electrons. Again, though, we do agree with Bohr that we need to have 8 valence electrons so that way we can have a full valence shell. We do agree with Bohr when it comes to that. Again, though, there are some exceptions to the rules, and we'll get to that exception in just a moment. But one more time. Now it says, remember on the previous page, letter A, C, and D, which was correct? Let's do those Bohr models from the previous page in a Lewis dot structure. So let me turn around and let me look at letter A. Letter A had, I don't care how many inside electrons, the only thing I care is the outside, which is only 1 valence electron. So for that situation, letter A would be 1 valence electron. It would be an element, I don't have a clue what it is, whatever element that is, and all I have is 1 valence electron. Now, because I told you earlier today that, hey, this periodic table is so cool. If we ignore the middle parts, or we call them letter B's, and you look at all the letter A's, that is going to indicate the number of valence electrons. So who could that be? That could be hydrogen, lithium, sodium, potassium, rubidium, cesium, or francium. It could be one of those. Who is this guy right here, letter A? I don't know, but it's one of them. So that is going to be number A. I guess I should have did that. Let's look at letter C. Letter C. Go back. Letter C has snap.
No, let us
3.
right there.
Oh, okay. I was looking at the wrong one. C's. 1, 2, 3. C. 1, 2, 3. Letter C is in group 13. So when I go to group 13, or we call it group 3 for short, it can be boron, it could be aluminum, it could be gallium, it could be indium, it can be thallium. It could be one of those. Who is it? I don't have a clue yet who it is, but that's who letter C is. Let's look at letter D. Turn back. How many valence electrons does it have on there? 2. Okay. 1, 2. Letter D has 2. And letter D is from group 2. Who is it? I do not know at this moment, but it's somebody from group 2. Now, which elements above have the same number of valence electrons? Ooh, none of them. None of them. If 2 elements have the same number of valence electrons, what does that mean? That means that they are from the same group. And I'm going to put a little arrow right here. Groups are the up and down columns. Groups are the up and down columns.
What are the other ones called?
Rows. They are rows, and these are groups, or you probably heard this word before, and when you were younger, or family. They're in the same group or family, which is the up and down column. The others are the rows. Or periods. Yeah. You write a sentence sideways and you put a period at the end. Groups, columns, families, rows, or periods. Alrighty, let's keep going. Oh, we're not done. Now, some atoms are actually a little different. Okay, not all atoms, not all oxygens are the same. You could have 2 different oxygens, for an example. So it says over here in our notes, Mendeleev, who is known as the father of the periodic table, because again, when we were coming up with all these models of the atom, we had a whole bunch of scientists who were trying to come up with the correct model of the periodic table. So Mendeleev gets the credit as the father of the periodic table. It says here, which are arranged in elements based on atomic, he did it mass, not atomic number. It says, look through the modern periodic table now. Do you see at least two elements that would have not been arranged correctly? So Mendeleev, one more time, is considered to be the father of the periodic table. Well, you know what, Dad? You're wrong. Because he arranged the elements based on atomic mass, not atomic number. There's actually two elements that in that situation, if you look at the current one, which would be arranged in the wrong way. Ni and I, iodine and nickel, are actually would be arranged incorrectly if we went with what he said. Now, he was great at the time, but again, modern technology, modern, just more science, we are able to figure out that Moseley, Henry, and back in 1912, discovered that there's two elements that contain different numbers, it says here, of protons. And now he put the periodic table in the correct order that we use currently, which is the atomic number. Mendeleev, you get the title, but you're not correct. But again, though, it's not that, these other scientists in the past were just wrong. Yeah, they were wrong, but they did try. They put that effort into it. Modern technology are disproving some of them, okay? The atomic number, we know it says here, is the number of positive protons in an element. Don't forget, all elements are considered to be electrically neutral, which also considers to be the same number of electrons, unless otherwise stated. So it says here, how many protons does an atom of gold have? Well, if you went to the periodic table and looked, it has 79 protons. What about an atom of aluminum? Aluminum is atomic number 13, so it has 13 positive protons. But how many electrons does an atom of gold have? Because they're considered to be electrically neutral, it has 79, and aluminum is considered to have 13, unless otherwise stated. I can't stress that enough. Unless otherwise stated. Alrighty, turn the page. Because this is where we're going to get into helping us when it comes to our homework. So it says here is where we are about to get to otherwise stated. Isotopes. It says that isotopes here are going to be atoms of the same element, but they have actually different number of neutrons. And that's where we're going to get that otherwise stated. We're going to have some little bit of exceptions to the rules. It says here, isotopes disproved Dalton's theory. Okay? All atoms of the same elements must have the same number, it says here, of protons, but not necessarily the same number of neutrons. We're starting to get to this otherwise stated issues, okay? So an example, potassium. Have you ever looked at, and I mean, you may not because you're like, I don't got time to worry about that, Miss Munson, but here's potassium over here. And so when we look at potassium over here, there it is. It has 39.098. Okay, calcium 40.078, rubidium 85.468. Why are all of these bottom numbers with decimals? Well, they have decimals because there's different types of potassiums. So potassium has an atomic number, I'm going to put right here, atomic number, potassium of 19. On the periodic table. atomic mass of, go back over here, 39.098. 39.098. Okay? Now, the reason why all elements have a decimal point when it comes to the mass number is because there's more than one element out there. Okay? If you go and look at your actual average or your grade, did you see when you took your test? It was like 88.763. Well, obviously, in that situation, if you took your test on D2L, it was 88.763. I rounded it up to an 89. Okay? So your grades, when you have it with your teacher and you look at your report card and you're looking at that paper and it says, oh, your report card or your progress report shows that you made a 62 or you made a 92. Did you really make a 92 flat? No. Did you make a 62 flat? No. You could have had a 61.76 or you could have had a 92.01. So they rounded. Why do they round? Because you have more than one grade. If you had one grade for the whole semester or the whole 6 weeks or 9 weeks, it would be one solid grade. But here, we don't have just one potassium that exists on planet Earth. We actually have three different types of potassium. Why? Because remember what I said earlier this week? These elements have been here since Earth has been created, and these elements have aged, okay? And so since they've aged at different times. So we have, at this moment, we have three different types of potassiums that we have found on planet Earth. We have potassium 39, we have potassium 40, and we have potassium 41. Now, when we add up all of the potassium on Earth, we have found that 93.25% is 39. We have found that 6.73% of the potassium is 40, and we have found 0.12 potassium is 41. We add the percentages together, and they should equal 100%. Okay? It's pretty easy math, I promise you. Now, we call these, one more time, isotopes. An isotope is going to be an element of the same element, but they have different neutrons. They have the same number of protons. Okay? So when we look at this, potassium, whether you're potassium 39, you still have 19, that's my magic number, protons. If you're potassium 40, you still have 19 protons. If you're potassium 41, you have 19 protons. I don't care what potassium you are, you have 19. For an example, when you get your driver's license, whether you're 16, 26, 46, or 96, you will still have the same driver's license number all the way through the end. That number is never going to change. Same thing here. As my potassium ages, I have the same number of protons. The neutron number does change. What this means over here is that I'm going to get the number 39, this mass number, and that's what this 39, 40, and 41 is. This is telling me a mass number here, here, and here. So I'm going to get the number 39, subtract it from the number 19, and it tells me that this potassium 39 has 20 neutrons. Let's do it again. But this situation, I have 40 as the mass number. Subtract number 19, which never changes. Now, I agree, I have 21 neutrons. And then, for this situation, I have 41 as the mass number. Subtract 19, which never changes. 41 take away 19 is 22 neutrons. So the neutron number, you can see for all three of the situations, actually changes. The neutrons, let's go back to recall what we talked about earlier this week. The protons and the neutrons are the mass of the element. Look at it. As an element ages, it actually can have more neutrons. I don't know, but if you have your driver's license, let's say at the age of 16, do you think that the mass or when you stepped on a scale at 16 with that driver's license number, is gonna be the same scale number when you step on at 36? Probably not. You may, between 16 and 36, gain a little bit of weight. Same thing over here as elements on the periodic table. As they age, they gain weight. And where do they gain weight? Could they gain it from the proton number? No, because the proton number will never change. Where can they gain weight? The neutrons. There you go. The neutrons can be added, and now it gains mass. The electrons, unless otherwise stated, the electron number is always going to be the same as the proton number, which is 19 for this situation, unless otherwise stated. Okay? One more time. The word isotope means it is still going to be the same. You are still the same person. Taj now at 15, 16, 17, 14. I was trying to get, we're videoing, I was trying to bump it up for you. Taj at 14 is the same Taj when he is going to be 34. He's still the same person inside. He who he is who he is. He's still going to be the same person. Just like potassium. As potassium ages, he is still going to be the same potassium. He just may gain a little bit of weight. Okay? Now, it says that there's two ways to write this symbol, and this is the part of the homework that I left blank. So if you're writing the isotope symbol, there are two ways to write the isotope symbol. You can write it like this, or you can write it like this. If you write it this way, this number right here is the mass number. If you write it this way, the top number is the mass number and the bottom number indicates the atomic number, don't forget, which is the proton number. So now I'm going to pause for a moment. I'm going to go back myself for us and go back to the homework. Because remember, I left that part blank because we needed our notes. So here we go. Back to strontium. When we look at it, it has an atomic number over here of 38. That's never going to change. So we are going to write isotope symbol. I'm going to put SR. You have two ways that you can do it. It's up to you. But I know that the top number from my notes, it says here is the mass number, and my mass number is 87. The bottom number is my atomic number, which is 38. Or you can write the full word out. So the full word, so I don't screw that up. Let me make sure. Stromium, I don't even know if I have enough space for it. Stromium dash, and then the mass of 87. I just don't have enough space. So your choice. But does that make sense now in the homework? Because I don't want anybody to be like, oh, I didn't know this one time. So let's do the other one that we did. Phosphorus. P. Phosphorus. So when we look at phosphorus, P.
82? Wait.
Oh, that's 87. There, sorry. Like I said, there's not a lot of space. There wasn't a lot of space, sorry.
No, you get it.
So phosphorus, the top number is the mass number, which is 31, and the bottom number is going to be the atomic number, which is 15. I like to use this one because I don't have to write out the full word. It's a little bit shorter and faster, less writing. But if you prefer to write out the full word, you're more than welcome to, okay? So that's where this part of the homework comes from. Now I'm going to go back to the notes. So that way we can finish this section over here, and then we'll do a little bit more, and then we are good to go. But I just wanted to make sure that we are ready for our homework number 1. Keep going. We've already talked about this, but it's a reminder that that mass number is the number of positive protons as well as neutral neutrons added together. Isotopes, they have some similarities, it says here. Chemically and physically, they are alike. The number of electrons are determined by that chemical behavior. Remember, the valence electrons is where all the chemical bonding occurs. Now, isotope similarities, it says over here, that they are also, not only have that same number, but it says they have the same number of positive protons as well as negative electrons unless otherwise stated. I can't use that word enough. Isotopes, they do differ. Where did I just say earlier? They have different number of neutrons because they age, they gained neutrons, meaning that they gained mass. They also have different mass numbers or different mass amounts. And they also have different, we can just call it masses. They have different mass numbers, they have different masses. And we can come over here and we can look. We have this mass of 39, this mass of 40, this mass of 41. This one has 20 neutrons, this one has 21, that one has 22. Let's keep looking. Let's look at this neon.
What does that say after mass?
I just wrote a line, I actually wrote those two words, flipped. This one's supposed to be mass number, this one's supposed to be masses. I just wrote them in the wrong spot. Yes, sir. So now practicing. This is just like our homework. Let's look at it. Neon. Neon, they told me, has a mass of 22. I need to go to the periodic table. Neon is a noble gas, and neon has an atomic number of 10. Now, this neon is always going to have 10 protons, no matter what. Unless otherwise stated, it is always going to have 10 electrons. The number of neutrons is going to be 22. Take away 10, which equals, there you go. This, aww. And neon is going to have a symbol of Ne. That's what this periodic table tells me. The top number is the mass, 22. The bottom number is 10. Easy cheesy. Calcium. Calcium. Calcium is Ca. Ca. Calcium has an atomic number of 20 from the periodic table, 20. That means that it has not only 20 protons, but it also has 20 electrons, unless otherwise stated. Now, they told me that there's 26 neutrons, so the mass number is 20 plus 26, which equals
46.
boom. So for my calcium, 46 goes at the top and 20 goes at the bottom.
Alright, so I'm just curious.
Yes, sir.
I thought the protons determine what element it is, but
That's true.
otherwise-
No. Nope, the proton number still determines what element.
Isotopes are the same elements with different masses.
What happened? Did I misspoke?
No, he didn't say shut up. Anyways.
Oh, no, tell me.
So electrons. Okay, I get it now. I
You
was just
sure?
wondering. Yeah, I get it.
Okay, because sometimes I misspeak, like I say.
No, I was
get my
just
words
curious because you
twisted.
said otherwise stated while writing protons. I was like, okay.
No,
that's
no,
cool.
oh,
But
maybe
no,
I was-
electrons and or neutrons, if otherwise stated, will be different. Okay.
Correct. One more time. The proton number will never change. The neutron number can change if we're talking about an isotope. An electron number can change if we talk about, we haven't talked about it yet, unless otherwise stated, that will be coming up soon, ion. Okay? But we haven't talked about it yet. Let's keep going. Oh, this one. They didn't tell me what element, but they told me the atomic number. That atomic number is the proton number and the neutron number. That number 8 on the periodic number is oxygen. This one is going to have an oxygen O. The mass number, is 17. Let's put that in. And the atomic number is 8. How many electrons is this going to have? If it has 8 positive protons, it's going to have 8 negative electrons, unless otherwise stated.
It's in the,
Wait, so protons and neutrons, the atomic number is 8.
it's in the 16 group, so it has a valence electrons of 16.
Shouldn't the neutrons be 9?
Thank you. I was waiting for somebody to speak up.
Yeah.
Because why?
Because
17 minus 8 is 9.
There you go.
And so that means we have to change the one over there, right? Also?
So that means that this situation, the mass number stays 17, but the atomic number still stays 8 because the atomic number is the number of protons. So that is going to stay, this is written correctly. That's the only thing that needed to change because 17 take away 8 equals 9. All right, let's do it again. Okay, proton number. Can the proton number ever change? No. That proton number is the same number as the
Electron.
atomic number first. But it will be the same number as electrons unless otherwise stated. Now, the mass number is the mass of the protons and the neutrons added together, which is 50. There we go. And if we look at number 26 on the periodic table, the number 26 comes out to be iron. Iron has a symbol of Fe. The top number is always the mass number, in this situation 57. The bottom number is 26 because that number will never change. Let's do it again. They gave me zinc, Z-N, zinc. Zinc for this second to the bottom row. Now I go to the periodic table and I can see that zinc, which is a metal, zinc.
oh, right here.
You swear, we're here. 30.
2B.
2B, zinc. It has an atomic number of 30, which is always going to be the proton number 30, and unless otherwise stated, it will be 30 as the electron number. But when I look at this mass, it says over here is 64. So, whoa, because they told me it's 64.
But it's 65.
Oh, but they told me otherwise stated it's 64, so I'm going to put 64. What could change? The neutron and electron numbers can change. If the neutron number changes, then that causes the mass to change, right? Uh-huh. So if we have 64 as a mass number and 30 protons, then we have 34 neutrons. Why can a neutron number change? Because it could be an isotope. For an example, Christian's twin came in, an isotope. Does that make sense? Yes.
So neutrons bounce out the electrons.
The neutrons balance,
Yeah, which ones do they balance out?
they don't balance nobody out. They are inside the nucleus, so that way they can be like pillows to buffer out the protons so they don't repel each other.
So that means if I have that many neutrons, I can add protons to
You could try, but will it hold? No, it won't hold. They know who they are. You can go and try to change a person, but if they know who they are in their gut, they are who they are. Does that make sense? Same thing. Somehow these elements know who they are, and they don't change for nobody.
That's what science is confused about.
I mean, you can try to change lead to gold, but you're not going to change lead to gold. Lead knows lead is lead. You can't change me to gold. I'm never going to change who I am
Actually-
and my gut.
Technically, if I was Midas, I would never change you to gold. So that's.
Well, Midas is about as real as Santa, but let's keep going.
I can have powers if I want.
Let's keep going. Last one. Who is number 80? Mercury. Mercury's symbol is, huh?
Oh, wait,
The symbol,
HG.
HG. HG. Now, where did we get Mercury from? Well, remember, unless otherwise stated, which we have not talked about, the electron number is the same number as the proton number, which also represents the atomic number of 80. Going over here to the periodic table, Mercury has an atomic mass. Forget this periodic table. We're going to look at what they gave me. I'm going to add 80 plus 124, which equals a number. 24. 204. 204. And so in this situation, 204 on top and 80 at the bottom. Easy cheesy? Okay. Yes, sir? That's a lot of neutrons. All righty. The atomic mass, it says over here, is the weighted average mass of the isotope of that element. So we have a math equation we will do later on. Have a great day. Yes, have a good one.